For you, that whole packet. Can't get this camera to flip. I think it's correct. Shows the inverted image on the board. Did you get an invite from me?
Yeah.
Can you tell me what it looks like? You click on the meeting.
So it's actually like all by.
Did you already download the app? Oh, it's downloading. Point it to you. Now, does this look correct to you? Oh, okay. So it's just backwards on my preview. So that looks like here. In other words, if you're standing there and you raise your right hand, your left hand goes up. So to me, the board looks wrong if I'm staring at this, but to you viewing it, it looks correct. Yeah. So then the only thing you want to do is mute yourself, so you won't hear echoes.
Okay. It said it unmuted. That worked.
I just muted you. So you unmuted you, I think. So now you should have a microphone with a line through. That means you're muted. Because if you're in the same room that it's broadcasting from, there's a time delay, so you hear all those echoes. Looks good enough? Well, you and I are the ones logged in, so if you click on the right hand side, you'll see participants list. You can see who's on. And then there's also chat, like if you wanted to type in a question. It's mainly for my office at home. So then my recording did work last Wednesday, but it's too big to send via email. So then I was looking at trying to post it to YouTube, but I've got to convert the RTF file to something else. So as with technology goes, I gave up because I didn't have the time. But at least it works. Okay, so as promised, you have pages for what? That's two. All right, Angela, do you have any questions? What you got? That's E1 and E2 and bases and nucleophiles, and you got it all. All right, chapter 8 is reactions of enes. Over three main ones or four main ones today. So for a quick review, how do we make enes? From halides by elimination. Could it be E1? Could it be E2? And which halide favors E1? Tertiary. What type of base favors E? Big, bulky bases. And what type of halide favors E2? Secondary or primary? And again, what type of base would you use if you wanted E? Big, bulky base. And what's the example we use over and over again for a big, bulky base? Potassium tert butoxide. That's KOTBU, if you were just writing out. Or symbolically, structurally, it's tert butanol. It's H with the potassium instead. And so if we want to emphasize elimination, we don't use a good nucleophile. We use a big base. And if we forget why I asked, if we're trying to make an alkene from a halide, do we want to do nucleophile reaction or elimination? Elimination. So elimination always requires a base, and the product is often an alkene. And that leads to chapter 8, which says, well, make sure we cover chapter briefly. Alkenes can be cis or trans, and those are called stereoisomers. This time did we learn another trick with E and Z. And chapter 8 focuses on reactions of alkenes and Markovnikov and anti-Markovnikov. And is Markovnikov's rule to be memorized so that you know the overall reaction? And should we also understand it from a mechanistic viewpoint? Yes. So we're going to do that in a minute, but to introduce one key topic that I didn't talk about is defining those two words. So stereospecific versus stereoselective. It really comes down to if you understand the word specific versus selective. And then after that stereo. Hard to put into words. Grasping for some right now, don't have. So an example, would you say those two are different stereoisomers? Which one's cis? And which one's trans? Which one would be E? E is trans and Z is cis. And if I say we're going to do an addition, we have an alkene, and alkenes tend to do addition. That should make sense. Additions can happen in a mode which is either anti or syn. That's syn when the two groups income from the same face. Anti is when the two groups orient from opposite faces. So, for example, say that those CLs, did we do chlorination first off? Yes, we did. And is chlorine one of those things that can add to an E? And when you add to an E, what happens to the double bond that was the E? Goes away. So do we then get that dihalide? And would you say the two chlorines are syn or anti to each other as pictured? Anti. So that mode of addition is anti. And what about that one? Still anti. So would this process be stereoselective or stereospecific? Specific. Because one stereoisomer with one mode gives only one type of stereoisomer product. The other stereoisomer by the same mode would give the other product. Other, we would have to do RNS and configure, etc. And that's not the best example because what do we know about these carbon to carbon single bonds once they are formed? There's free rotation, so is this really fixed in the anti slot compared to that, or can that rotate? that rotate. So I was just exemplifying if this is like that, the addition occurred as an anti. It occurred some anti and some sin. Then you, but one or the other was favored. Then the process would be stereo selective, meaning you get some of each, but you get a predominance one over the other. But if you get one type of isomer from one isomer, then it's stereo. So where the example can be more full is if I go with that. So first off, we've got to know this adds to an ene. And that's what we're going to get without any stereochemistry consideration. And that's the most important thing to understand. Enes do addition, that's what we're going to get. Now, if we say this chlorination occurs as syn, would we say those are going to come in from the same phase? If it occurred by anti, would they come in from opposite faces? If you get one only, then the reaction would be called what? Stereospecific, because you only get one. If you get a mixture of both, but you get a predominance of one over the other, stereoselective. So if I tell you this is the only one we get, that's the only product we get, would you say chlorination is then stereo specific? And does the mode occur by anti or syn? Anti. Because are the two chlorines from the same face or from opposite faces? And now that one's a much better example. Does this carbon to carbon bond have free rotation? It does not, because it's cyclic, and if that bond were to rotate, would the ring have to break in two? So because of torsional strain, you can't get free rotation, and then those chlorines get in their cis or trans configuration. That's a question. Is that cis or trans? That's trans. Is this the cis or trans isomer? Actually, neither, but right. This group is actually the same as that group, so technically it's cis or trans. So we're going to understand all that when we say mechanistically the first step in chlorination or bromination or iodination is nucleophile and attack. And to make things easier or harder, I'm not sure which it's going to be, as attacks, and that leaves is so this nucleophile is going to make a new bond between that C, which is that C, and this Cl, like so. And this pair is going to make a bond between that same Cl and this C, which is that C. And how many pairs will stay on the Cl? One. And where will this go? And lastly, who will be positive? That Cl. Because this Cl gained a pair, lost a pair, and lost a pair. So if it lost a pair and lost a pair, it would be +2. But since it gained a pair, it's only +1. And what about this carbon? Did it lose that pair? Or does it still have that pair? That carbon has this pair, and that pair is now there, so that carbon still has that pair. So would its charge change? No. This carbon, did it lose this pair? As this pair became that pair. So you would think this carbon would be positive, but did this carbon also pick up a pair? Did this carbon change its charge? So that's how you track charges with mechanisms. And this is classic. It's called a fluorinium ion. All right, why ion? Because it has a charge. Why fluorinium? Because it's a positively charged chlorine thing. And what would you say happens now? Now it's really helpful to know where you're going. Because the second chlorine attached to the same carbon as has the initial chlorine or to the other carbon. And if I draw arbitrarily as out at you, would this come in from that same face or from the back face? And so as it comes in, is coming in from the back face. So does that chlorine and that chlorine end up opposite to each other? And now can it rotate? No. Can it chair flip? Sure. Would you end up with one axial and one equatorial and they'd have the same stability anyway? So what's the value of mechanisms? It helps us understand our stereochemistry during the course of a reaction. And is there an analogous brominium ion and iodinium ion? Or if we were adding bromine or iodine. Good with that? So that's an example of a stereospecific, and the mode of addition is anti. And so do you get this isomer from that isomer? So we'll use that one again. So now we look at hydrohalogenation. And what would you say the first step in completing your mechanism is? To draw out the bonds of your hydrogen fluoride. And who's going to attack who and how? And now you're into another topic called regiochemistry. And now we've got to say, unlike chlorine, which is symmetrical, is HCl asymmetrical. And so now do we have to consider the orientation of these two things to an asymmetrical ene? And so if we're going to do addition, could we get that? And could we get that? Is that stereochemistry or regiochemistry? That's regiochemistry. And Markovnikov's rule, what? When you're doing an addition, and the addition involves H, the carbon with more H's preferentially gets the incoming H. So are we doing an addition where H is a part of it? And can you count the H's on each carbon? How many H's on that C? None. How many H's on that C? One. Which C has more? So which C preferentially gets the incoming H? And which product is that? This one. Regioselective. So this is called the Markovnikov product, and this is called the anti-Markovnikov product. Would we get like an 80-20 mixture of both? Something. And have we even dealt with the stereochemistry yet? To really understand both of those, you propose a mechanism. And in your proposed mechanism with all of this, should you embrace the concept of, is your ene going to be a nucleophile or electrophile? Is this, your ene, going to be a nucleophile or an electrophile? Always be your question. The nucleophile. That line or that pair of electrons always represents a hypothetical negative, correct? And negatives are in HCl, is it polarized like that or is it polarized like that? And does HCl have to be your electrophile because this is already your nucleophile? And what makes anything an electrophile? Some positive characteristic somewhere. So now who would you say is going to attack who and how? Do electrophiles attack nucleophiles or nucleophiles attack electrophiles? Nucleophiles always attack electrophiles. Because when we say attack, we're attacking with a pair of electrons. And who has the electrons? The nucleophile. What do nucleophiles tend to go after? Positives or electrophiles. And then you want to add that to which carbon would you say is more negative, or said another way, is less positive? And that's very, very hard to see. So let's start with this is going to grab the H, not the Cl, because this is hypothetically negative and that is polarized like so. And when this pair of electrons grabs that H, will that bond break? And arbitrarily, could I show what I drew as an arrow like that? And like that. Because right now, in this, those two carbons share that pair of electrons. When I make an arrow grabbing an H, that could be this or it could be that, either one. And now we got to account for tidying up some charges. If this bond breaks like that, what else will be generated? A Cl minus. And if we've generated a minus, does something have to be positive? Then go into here where would be the positive locale. Well, who shared these electrons? Those two carbons. In this product, who still has these electrons? This carbon or that carbon? These electrons are those electrons, correct? So does this carbon still have its share of those? So who would be positive? If this becomes that, same question. Who still has its share of its original electrons? That carbon. Who doesn't? That carbon. Who would be positive? And at long last, now you should easily pick up on what? Now you're back to what we did 3 weeks ago. Are those both carbocations? And what is our order of stability for carbocations? Primary are the best, tertiary are the best. And then that should ring bells in your head saying, oh, well, let me consider what type of carbocations those both are. So there's the carbon, which is the carbocation, and that carbon has how many other carbons directly on it? So that is and in this one, there's your carbocation that has how many carbons on it? 3. So which carbocation is going to be favored? That one. And when we then reconnect this chloride to the carbocation, that leads to which product? So why do we get more of it? Because it passes through a more stable intermediate than this one. So is Markovnikov's rule really just disguised carbocation stability rule? But what do we call it? Markov-Nikols's rule. So you can either try to memorize it or learn it by doing mechanisms. Which do I suggest? Markov-Nikols's rule says the C with more H's preferentially gets the incoming H. If we say, why does it happen? Because it proceeds through more stable carbocation. Any questions on that one? One more time. So if we were to do that, what are the products that are possible? Those would be possible products. And which one is favored by Markov-Nikol? That one. Because on your ene, which carbon has more H's? This carbon has a methyl that has two methyls and a carbon, so that's the only H in the molecule. So which C of your ene has more H's? This one. Which C gets the incoming H? That one. And so that one is leading to this product because your Br is off this carbon. So preferentially, is that the orientation that they'll add, or is this the orientation that they'll add? Like this. Because this C has an H, this C doesn't, so this C gets the H, this C therefore gets the, and so you would just do that, and you've got your product. If we want to understand it mechanistically, then do we do that? That? And in this intermediate, where would the positive be? On that carbon. And what type of carbocation is that, since it's connected to three other carbons? Tertiary. And then when the Br comes back, again, we're at this product. And what we just described is the regiochemistry. If the mechanism does proceed through this carbocation intermediate, would you say it's going to be stereo, selective, specific, or random? In other words, if I look at this Br attacking that carbocation, could it do it from that face, or could it equally do it from that face? pretty much equal from both faces, so it's definitely not going to be stereo specific. It may be stereo selective or it may not be stereo selective at all. So with all of these, you got all of that to consider. So once you get the general theme, it's going to get easier. This is going to be example of acid catalyzed hydration. If we do acid catalyzed hydration of an ene, you're going to add H and OH across the double bond. And if you're going to add H, whose rule is going to apply to the regiochemistry? Markovnikov's. And same question. C is going to get the incoming H. That C or that C? That one, because that C has more H's right now. It's going to get the incoming C, and it's going to get the OH then, the other C. Do I have to draw this H in on that C, or can we see that it's there? Hope we can see that it's there. That's the Markovnikov hydration product. What would be the anti-Markovnikov? And would you say those are stereo or regio isomers? Regio isomers. And if this does proceed through that carbocation intermediate, how would that form? This is where you have free will. That's water. Who's that? A proton. And does the proton have any electrons? If I say, how would this and that get to there? Correct. And if we were to propose that happening, would you again generate an H plus and OH minus? So whenever you're dealing with water chemistry and organic, you can use just plain water, you can use hydronium, or you can use hydroxide, or you can use a proton if you're proposing a mechanism. If I go with which of these is the most electrophilic, so if you want to find an electrophile, think positive, would you choose this for an electrophile? This, this, and this. So if I'm going to take that ene and make this intermediate, is this our nucleophile or electrophile? That's your nucleophile. And is it always going to attack something? And that something then is the electrophile. Could you simply use this as your electrophile? Could you simply use that as your electrophile? Good. Could you use this? Either way, I mean, that's the simplest. If I say let's use hydronium as the electrophile, which part of the hydronium is going to get connected to this C? H. And then which way do those have to go? Back to O. Then you've made water, and you've moved a proton on that carbon. And if we move a proton onto that carbon, which of those carbons no longer has its share of those electrons, and thus is a carbocation? That one, and what we have here. So to get from here to here, you've got to realize this C is going to pick up an extra proton like that. Good with that? And then in this carbocation intermediate, is it chiral or achiral? Not chiral, achiral. So when the OH comes back in, could it come in from that face or just as equally from the opposite face? And so is this intermediate going to be acted on stereospecifically, selectively, or random equally from both sides? So then the regiochemistry is dominated by Markovnikov. The stereoselectivity or lack thereof is dominated by the mechanism. The important part of that one, other than what we just said, is that how we make alcohols from enes? How else could we make alcohols? From halides and water. So again, we're just building up our repertoire. Now the bad news would be, if you have an organic molecule that you've worked hard for and it has other functional groups in it besides the ene, could the strong acid conditions required for hydration cause problems in the other areas of the molecule? So during the 1900s, did we constantly look for new and more efficient ways to do the same reactions we did in the early 1900s? And then once we found a way, did we figure out a lot of other stuff incidentally? So oxymercuration, demercuration is a way to do the same reaction we did, which would be called hydration of an ene, to give the Markovnikov product, only it avoids using those rather harsh conditions. So mercuric acetate and water. Those are that's your reagent, number one. And then you follow that up with sodium boryl hydride, which is your demercuration step. Mercuric acetate, it like that. So there's a coordinate covalent bond there and there. And if one of those acetates pops off, you can have that species, which gives you a way to say, aha, that's my electrophile. So if I go with our same ene, where is mercury preferentially going to end up? So just like this, which carbon preferentially grabs the positive proton? That one. True? Which carbon ended up positive when this carbon grabbed the proton? The top carbon. So typically it's the same. Which carbon's going to go after the positive mercury? The bottom. Which carbon would end up positive? The top. And that's because it's tertiary level. And then you have that. And water is the key player in oxymercuration, demercuration. So the next step is to just take hydroxide and add it to that carbon. And now you have an intermediate, looks like what? And then for the fun times, sodium borohydride is a source of H minus, and it's a good reducing agent, and it just knocks off all of that as H minus comes into that same carbon. So if we knock off the mercuric and the acid part and replace that whole chunk with H, do we get this product? So is that the Markovnikov product or the anti? Markovnikov? Markovnikov says which ene carbon has more H's, which preferentially gets an incoming H if we're doing hydration. The bottom, which therefore gets the OH. So this is the Markovnikov. So oxymercuration, demercuration uses how many reagent systems? Two. The first step is mercuration, and it's oxymercuration because oxygen is on the mercury. And the second step is called demercuration because in the second step, does the H minus knock off the mercury species? So why would we do that when we could just use water and acid? Because water and acid is going to be more harsh with other areas of the molecule. Oxymercuration, demercuration are milder conditions, less likely to cause unwanted reactions elsewhere, and more efficient. That's basically the bottom line. And the next time we're going to cover the Nobel Prize for H.C. Brown, who figured out a reagent system which uses boron that gives the anti-Markovnikov product. So why was that so valuable? Because pretty much everything before then gave you the Markovnikov hydration product, and now hydrogenation oxidation gives you the anti. So what we did today was sort of dive into some more mechanisms, but also did we figure out how to make alcohols from enes? So that would be hydration. So on that last series of sheets I gave you, that has that graphic that looks like that. So you see the center of all the arrows is an ene. So if you go up to the right towards 1 o'clock, which alcohol is Markovnikov? One on the left, and the one on the right would be called the anti-Markovnikov. So the Markovnikov alcohol is primary, secondary, or tertiary? And the one on the right, the alcohol is primary. And you'll see when we get to oxidation, those are going to give very products as we move forward with oxidation. So basically, when we get done with chapter 8, we'll be all of those reactions. As soon as we finish with chapter 8. You in a hurry? So down at the bottom are all key terms that we're going to get used to using. Hydration, we covered today. Hydrogen halide addition, halogen addition, Markovnikov, anti-Markovnikov. Are we going to incorporate mechanisms so we can understand syn and anti? And stereospecific, stereoselective, regio, and selective and specific, chiral and prochiral. Those are all things already. Anyone got questions? What are we doing in lab today? We are making esters. So your assignment for pre-lab is to pick an ester to lots of choices in your packet. You can make paint thinner, or you can make something that is fruity and is found in flavorings, or you could make ethyl acetate, a solvent. So if you choose before lab, then we'll make more efficient time of lab. regardless of which ester you choose, it's a reaction between an alcohol and an acid. And then work up as usual. You like wintergreen?
Oh, the gum. Oh, the one that kids swallow.
Yeah, juicy fruit really is synthetic chemical that's in the juicy fruit gum. I don't know if it used to be very popular. I don't know if it is or not anymore. Okay, we'll see you at 1 o'clock. Yeah, we don't have class on Wednesday. 2 days from now. Not tomorrow, but the next day. Today is the 26th. They will pick up with hydroboration oxidation. I hope it's going to be saved, and I hope I can get it to the file. And if I can, I was going to post it to YouTube because when I checked the other day, the one I recorded last Wednesday, the file was too big to send out via email. So then I looked a little more in depth, and they get saved as an RTF file. Anyone know what that is? Yes. And then upload it to YouTube, you've got to convert it to an MP4 file. And so I got to figure out how or if I can do that conversion. I think what WebEx does is it records it and saves it in a file format that shrinks the size for transmission potential. So I don't know if I just stopped it or not. But I hit record again, so I know I stopped. Yeah, I just